In 2017, a small team at Google asked a strange question. What if language did not need to be read in order? That sounds wrong. A sentence comes one word after another. A paragraph comes one sentence after another. Recurrent neural networks were built around that fact. They read text like a person following a line with a finger. But that created a worm. The first word had to pass its meaning to the second. The second had to pass it to the third. If the clue sat 50 words away, the signal had to survive 50 handoffs. It was slow. It was fragile. It was hard to train at scale. Then the transformer paper made a clean bet. Let every token look at every other token at once. The formula was attention of Q, K, V equals softmax of Q times K transpose, divided by square root of D sub K times V. That equation became the core operation behind BERT, GPT, Claude, Gemini, Llama, modern translation, code models, image-text models, and the current industrial build-out of accelerator chips, data centers, and long-context software. The paper was about machine translation. The equation became a new way to compute meaning. If you want to know why modern models can connect it to a noun far away, why long context is expensive, and why GPUs became the factory floor of intelligence, this is the equation. Language has a long memory. Take a simple sentence. The animal that the old farmer rescued from the flooded barn was shivering. The word was belongs to animal. It does not belong to farmer. A human catches that link without thinking. A machine has to compute it. That is the puzzle. How does a model decide which earlier words matter for the current word? Before 2017, sequence models leaned hard on recurrence. Recurrent neural networks read tokens one step at a time. Long short-term memory networks, or LSTMs, added gates to help memory last. Gated recurrent units did much the same with fewer parts. These models helped machine translation, speech recognition, and text generation. They were useful. They were also bound by order. The model could not fully process token 50 until it had processed tokens 1 through 49. That made training hard to spread across GPUs. It also made long-range links hard to keep clean. Attention already existed. Bottleneck attention in 2014 let a decoder look back at encoder states during translation. Luong attention refined that idea. Attention was a helpful add-on. The 2017 step was sharper. The Google team removed recurrence and convolution from the main sequence path. It kept attention and feed-forward layers. That was the bet behind the title, Attention is All You Need. The breakthrough was not that attention was new. The breakthrough was asking whether everything else could be cut away. The real problem was speed plus distance. In translation, an English word may depend on a German word far away. In code, a variable may be declared far above its use. In a legal paragraph, one phrase may change an obligation 3 clauses later. Recurrent models had to carry these links through a chain. That chain cost time. It also blurred meaning. By 2017, neural machine translation had made real gains, but the best systems still leaned on recurrent or convolutional structures. Training large models on long sequences was costly because the sequential path limited parallel work. The transformer paper reported a clean, practical result. On WMT 2014, English to German translation, the model beat the previous best results. On English to French, it reached a strong single-model score after training for 3.5 days on 8 GPUs. The number matters less than the mechanism. The mechanism let every position connect to every other position in a constant number of sequential steps. So the question became plain. How do you build a model where any word can reach any other word right away? People were using recurrence. The model read a sentence like a conveyor belt. Token 1 went in, then token 2, then token 3. Each hidden state carried a compressed memory of the past. This felt natural. It matched how text appears, but it forced meaning through a narrow channel. People also used convolution. Convolutional sequence models could process local windows in parallel. They were faster than pure recurrence in some settings, but a word still needed many layers to reach a faraway word. The path length grew with distance. Attention helped, but it was often attached to a recurrent body. The old workaround was to add attention to a sequential model. The new move was to make attention the body. That is the hinge. Once attention stops being a helper and becomes the main path, the whole shape of computation changes. This mattered because scale was becoming the product. If a model could train faster, it could absorb more data. If it could connect distant tokens, it could handle longer instructions, longer documents, larger code files, and longer conversations. If it could run as matrix multiplications, it could ride the GPU boom. That changed more than translation. It changed search ranking. It changed autocomplete. It changed code generation. It changed drug discovery models. It changed speech systems. It changed robotics policies. It changed the economics of cloud data centers. The equation did not create intelligence by itself, but it created the operation that could be repeated, stacked, widened, and trained at industrial scale. A formula for weighing words helped turn warehouses of GPUs into language factories. That is why this did not stay inside research labs. It moved into products, budgets, power bills, and chip roadmaps. The gap was simple to state. A model needed a way for each token to ask every other token, "How relevant are you to me right now?" That question leads straight to queries, keys, values, and the attention formula. The car starts with a token. A token can be a word. It can be part of a word. It can be punctuation. In a code model, it can be a brace, an identifier, or part of a name. The model first turns each token into a vector. A vector is a list of numbers. It is not meaning itself. It is a place where meaning can be worked out. Then, the model gives each token 3 roles. The first role is a query. A query is the question this token asks. It says, "What am I looking for?" The second role is a key. A key is the label this token offers to others. It says, "This is what I contain." The third role is a value. A value is the content this token gives if another token chooses to look at it. The plain picture is a library. Your query is what you type into the search box. The keys are the catalog entries. The values are the pages you read after the search ranks the results. In self-attention, the same sequence gives all 3. That is why it is called self-attention. The sentence looks at itself. Each token asks about every token in the same sentence. It can even ask about itself. Now give the parts their matrix names. Q is the matrix of all queries. K is the matrix of all keys. V is the matrix of all values. Each row belongs to one token. If the sequence has n tokens, Q has n query rows, K has n key rows, V has n value rows. The model learns how to make these rows. It multiplies token embeddings by learned projection matrices. Those projection matrices are trained from data, so the model does not use a fixed set of labels like subject, object, or verb. It learns its own search space. One head may track grammar. One head may track position. One head may track matching names. One head may track quotation marks. One head may track an earlier claim that the current word depends on. That is why multi-head attention matters. A single attention head gives one way to compare tokens. Multi-head attention gives several ways at once. The original transformer used 8 heads in the base model. Each head could learn a different relation. But the heart of this story is one head. One head is enough to see the equation. A token is not only a word in this system, it is a tiny search engine pointed at the rest of the sentence. Now we can write the formula. Then we can see how the search turns into arithmetic. Attention of Q, K, V equals softmax of Q times K transpose divided by square root of D sub K times V. Here, attention of Q, K, V is the output of one attention head. Q is the query matrix with one query vector for each token. K is the key matrix with one key vector for each token. V is the value matrix with one value vector for each token. K transpose is K turned so queries can be compared with all keys. Q times K transpose is the raw score matrix, where each entry scores one token against another. D sub K is the dimension of each key and query vector. Square root of D sub K is the scaling term that keeps scores from getting too large. Softmax is the function that turns scores into weights that sum to 1. Softmax of Q times K transpose divided by square root of D sub K is the attention weight matrix. Times V means a weighted sum of value vectors. This formula does 4 jobs. First, it compares every query with every key. That is, Q times K transpose. If token I has a query vector and token J has a key vector, their dot product is a relevance score. A large score means the query and key point in similar directions. A small score means they do not match well. Second, it scales the scores. That is, the division by square root of D sub K. Without this scaling, dot products get too large as the vector dimension grows. Large scores push softmax into a near one-hot state. One token gets almost all the weight. The gradients become tiny.
Training gets worse.
The 2017 paper gave the reason. If query and key parts have mean 0 and variance 1, then their dot product has variance D sub K. Divide by square root of D sub K, and the scale comes back down. Third, it normalizes the scores. That is softmax. Softmax turns a row of raw scores into a row of weights. The weights are positive. They add to 1. They say how much the current token should look at each other token. Fourth, it mixes the values. That is the final multiplication by V. The output for each token is a weighted blend of value vectors. The token is no longer just itself. It now carries context from the other tokens it attended to. In the original transformer, one common head dimension was d sub k equals 64. The scale term was square root of 64, that is 8. That small division kept the softmax in a useful range. This is the answer to the old sequence chain. The model no longer has to pass meaning down a long relay. Every token can score every other token straight away. Here is a small example. Take the sentence, "The bank by the river was steep." The token bank is unclear. It could mean a financial firm. It could mean the side of a river. When the model processes bank, its query can score keys from river and steep. Those tokens can get higher weights than unrelated tokens. Their value vectors flow back into the representation of bank. Now bank becomes more river bank than money bank. The same move can help with pronouns. In the sentence, "The trophy would not fit in the suitcase because it was too large," attention can link it to trophy. In the version where it was too small, attention can link it to suitcase. The weights shift with context. That is the power of the formula. It does not store a fixed grammar rule. It computes relevance from the current sequence. Meaning is not pulled from a dictionary. It is rebuilt as a weighted vote from the nearby tokens. But why does this work so well? And why did it beat the old sequence chain? We are not doing a formal proof. We are building the logic of the formula. Start with the task. For each token, choose which other tokens matter. That means we need a relevance score. The simplest learned score is a dot product. If two vectors point in the same direction, their dot product is high. If they point in unrelated directions, it is low. If they point opposite ways, it can be negative. So, we give each token a query vector and a key vector. The query says what this token seeks. The key says what another token offers. For one token, we could compute score sub I, j equals q sub I times k sub j. Here, score sub ij is the relevance score between token I and token j. Q sub I is the query vector for token I. K sub j is the key vector for token j. But doing that one pair at a time wastes the hardware. Put all queries into Q, put all keys into K, then Q times K transpose computes all pair scores at once. That is the first move. If a sequence has n tokens, Q times K transpose makes an n by n score table. With 1,000 tokens, that is 1 million pair scores for one head. That count comes before we even add layers or heads. Now comes the scale. Suppose each query and key has d sub k components. The dot product adds d sub k small products. When d sub k grows, the usual size of the sum grows too. Large dot products make softmax too sharp. A sharp softmax can help when the model is sure. It hurts when the model becomes sure for numeric reasons before it has learned. So we divide by square root of d sub k. This is not decoration. It is a stabilizer. It keeps the scores in a range where softmax can still show shades of relevance. Now comes softmax. Raw scores are not yet weights. They can be negative. They do not add to 1. They cannot serve as a clean mixing rule. Softmax turns each row into a probability-like row. If one token is highly relevant, it gets a large weight. If another token is weakly relevant, it gets a small weight. The row sums to 1. Now comes the value matrix. A key tells you whether to look. A value tells you what you get when you look. That split matters. In a library, the catalog entry helps you find the book. The book is the value. In a database, an index helps you find a row. The row is the value. So the attention weights multiply V. The output is a weighted sum of values. That gives the full chain. Need relevance. Use dot products. Need all pairs. Use Q times K transpose. Need stable scores. Divide by square root of D sub K. Need weights. Use softmax. Need context. Multiply by V. If you are thinking this is just a weighted average, you are close. The trick is that the weights are learned from the current sequence. They are not fixed in advance. This also shows why self-attention runs well in parallel. A recurrent model has to step through time. Self-attention turns the whole sequence into matrix multiplications. GPUs and TPUs are built for that kind of work. The original transformer also added position information. Attention by itself does not know order. It can compare tokens, but it needs position signals to know whether one token came before or after another. The 2017 paper used sinusoidal positional encodings. Later models used learned positions, rotary positions, and other variants. So, self-attention does not ignore order. It computes relations after order has been written into the token representation. The final model stacks layers. One layer builds local and global context. The next layer can attend over those richer representations. Layer after layer, the model builds deeper features. That is why a small formula can become a deep system. It is repeated. It is trained. It is scaled. The equation is small enough to fit on a t-shirt. It is also large enough to burn billions of dollars of GPU time inside it. The same all-to-all power also creates the wall. Every token can see every token, so the bill grows fast. Self-attention has one brutal wall. It is quadratic in sequence length. If a sequence has n tokens, Q times K transpose creates an n by n matrix. Every token compares with every token. Double n, and the number of pair scores grows by 4. That is not a bug, it is the formula. The same thing that makes attention powerful makes it expensive. For 1,000 tokens, one head has 1 million pair scores. For 10,000 tokens, it has 100 million pair scores. For 100,000 tokens, it has 10 billion pair scores. Now multiply by heads, layers, batches, and training passes. That is the context length wall. The second wall is memory movement. Modern accelerators are fast at math, but they can still slow down when they move data between memory levels. Standard attention may create and store large intermediate matrices. Reading and writing those matrices can become the bottleneck. That is why FlashAttention mattered in 2022. Treedow and co-authors did not change the formula. They changed how the formula is computed. FlashAttention tiles the computation. That lets it avoid writing the full attention matrix to slow GPU memory. It computes exact attention with far fewer memory reads and writes. The result was faster attention. It was also more memory efficient. It helped make longer contexts more practical, but it did not repeal the all pairs idea underneath. The third wall is meaning. Attention weights are not always explanations. A high weight means one representation used another representation strongly in that layer and head. It does not always mean a human reason. Many heads interact. Later layers change the output again. If you treat one heat map as the model's whole explanation, you can fool yourself. A model may put strong attention weight on punctuation, a separator token, or a nearby structural token. It may do that because the token helps the computation. It may not be the human reason for the answer. The fourth wall is data and objective. Self-attention gives the model a way to connect tokens. It does not give the model truth. If the training data is wrong, biased, stale, or thin, attention can link the wrong things with great confidence. The original problem was how to connect distant tokens without a fragile sequence chain. Self-attention solved that connection problem. It did not solve cost. It did not solve truth. It did not solve interpretation. The attention map can look like understanding, but first, it is a routing table. So the trade is not that attention is magic. The trade is knowing when all-to-all context is worth the price. Self-attention is not a mind. Inside the range where context links matter and compute can pay the bill, it is the cleanest routing engine we have. Use it when links run far apart. A legal clause may lean on a definition 10 pages earlier. A code function may depend on an import at the top of the file. A medical note may name a drug once, then name a side effect much later. A talk may turn on a promise made at the start. Self-attention is built for that kind of work. Use it when the model must weigh many choices at once. Search needs it, translation needs it, summaries need it, code repair needs it, retrieval augmented generation needs it, protein sequence work needs it. Multimodal reasoning needs it too. All of those jobs need flexible links. Attention gives the model a learned relevance table at each layer, but use it with care when context gets long. Long context is not free. If you add 10 times more tokens, the number of attention checks can grow 100 times. That cost hits compute. It hits memory too. Engineers have found ways to ease that pain. Sparse attention cuts down the set of comparisons. Retrieval narrows the field before the model looks. State space models change the design. Hybrid models split the job across parts, but the core trade does not change. All-to-all context buys freedom. It charges in compute and memory. That trade shaped the last decade of machine learning. The 2017 Transformer paper turned attention from a side part into the main sequence operation. BERT, in 2018, used transformers for two-way language understanding. OpenAI's GPT line used decoder-only transformers for generation. By the early 2020s, transformer variants ran search, translation, coding tools, chat systems, image-text models, and the new data center build-out around GPUs and accelerators. The equation changed software practice too. It made matrix multiplication the main workload of language intelligence. It made attention kernels a key engineering problem. It made memory layout matter. It made batching matter. It made GPU use matter. It made context length a product feature. And it solved the old problem in a plain mechanical way. The model connects distant tokens by turning each token into a query, a key, and a value. Then it scores each query against every key. Then it normalizes those scores. Then it blends the values into a context-aware form. That is the gain. Not thought, not judgment, routing. So here is the practical checklist. If the task needs long-range links, attention is a strong tool. If the task only needs local patterns, cheaper methods may do the job. If the context is huge, plan for the quadratic wall. If you inspect attention weights, treat them as routing signals, not full explanations. If accuracy matters, remember what attention does. It routes information. It does not check truth. That point matters more than it may seem. A model can attend to the right sentence and still get the answer wrong. It can route the right facts and still fail to reason well. It can sound sure while it blends bad evidence with good evidence. Attention helps the model see. It does not tell the model what is real. So the right question is not whether attention is powerful. It is. The right question is what kind of power you are buying and what it costs. You are buying flexible access across a field of tokens. You are buying a way for distant parts of a sequence to meet in one step. You are buying a system that can reshape its links from layer to layer, token by token, task by task. And you are paying for every one of those possible links. When the task needs that reach, the bill can be worth it. When the task does not, the bill can be waste. That is the rule that sits under a great deal of modern machine learning. The model that sees more is not always the model you need. The model that links everything is not always the wise choice. Sometimes the best system is the one that refuses to look everywhere. When you use a long context model, ask this first. Which tokens actually need to see each other? And am I paying all-to-all attention for context the model does not need? Self-attention says, each token should ask every other token what matters, then blend the answers with learned weights. The 2017 Transformer paper turned that idea into the operating core of modern language models, search systems, code models, and the current GPU data center boom. Use attention when distant context matters, but remember the bill. Every token, looking at every token, is powerful because it is expensive.